Hello, my name is Alexander. I am a mathematician programmer at C3D Solver Group. Today, I would like to introduce you to our main products, two-dimensional and three-dimensional solvers, and tell you about their main new features that we have implemented since last year's conference. Let's start with the two-dimensional solver. It allows to create a complex parametric sketches in the plane. For this purpose, we provide a large number of different geometric objects that could be bound by various constraints, both logical and dimensional. We also provide tools for analyzing degrees of freedom, dragging. The ability to log API calls greatly simplifies the process of describing problems in the service desk for our customers. In addition, the API of the two-dimensional solver is available not only in C++, but also in JavaScript and .NET platforms. The main novelty of two-dimensional solver this year is the appearance of a new type of objects. These objects are patterns. We understand pattern as a set of identical geometric objects placed on the plane according to some law. There is a leading element that usually called a sample, and all other elements are called copies or instances. Usually, CAD systems provide an opportunity for an engineer to create a large number of different patterns. At the same time, almost all of them are a composition of two types of elementary patterns, linear and angular patterns. That's why we have implemented these two types of patterns in Solver. Linear pattern is a kind of translational symmetry when copies are placed relative to the sample along some straight line at distances that are multiples of some step. While the angular pattern is a kind of rotational symmetry when copies are placed relative to the sample by rotating around some center and angular that are multiples of some angular step. We designed the linear and angular patterns in such a way that they provide two important opportunities. First, any element of the pattern could be bound to other geometric objects of the sketch by constraints available in Solver. And the law according to which the sample and its copies should be located will be performed automatically. It's also possible to impose any dimensional constraints on pattern elements. Second, this is an opportunity to make any compositional patterns combining linear and angular patterns. This slide shows example of such patterns built by combining linear and angular patterns and two linear patterns. In the API, we have provided two ways of working with patterns. The first way is presented on this slide. Using the example of creating a linear pattern, here we create a line segment when define a linear pattern using the addLinearPattern function, after which we create instances of the pattern as a new geometric objects that already belong to the pattern. The second way to create a pattern is shown on this slide, using the example of creating of angular patterns. It consists in already existing geometric objects to the pattern. This is done using the addPattern constraint. Another important new feature of two-dimensional solver is the ability to manage metric spline length. Now you can work with the spline length as an informational driving or interval dimension. You can also equate spline lengths to each other and impose a point by metric percent constraints on the spline. And now a little bit about significant improvements. First, it's now possible to limit the position of a point within a given parametric segment of the curve. This became possible due to the fact that now in the constraint point by percent on the curve, percentage can be set as a variable. And also because of the new constraint that called addBound, which allows you to limit values of a variable inside some interval. New tangency cases for ellipses have been edited. Ellipse and ellipse spline. We are constantly working on improving the quality of diagnostics of redundant constraints. This year, the most significant results were the results of searching for conflicting constraints that were created in a satisfied state. But any attempt to modify a sketch with such constraints leads to failure. This situation is especially frequent for dimensional constraints. This slide shows the most typical examples of redundant constraints, which we can now correctly diagnose. Now let's move on to the three-dimensional solver. It allows you to solve two types of problems. The first problem is a composition of three-dimensional bodies in an assembly. C3D Solver provides a wide range of logical and dimensional constraints for mating different types of three-dimensional geometric objects. It provides tools for analyzing degrees of freedom, logging, and dragging, as well as two-dimensional solver. A .NET interface of the three-dimensional solver is also available. Another task that the three-dimensional solver allows to solve is the construction of wireframes and pipelines. The solver provides functionality for creating line segments with varying length and arcs of circles with varying length and radius, and mating them with logical and dimensional constraints. Degrees of freedom analysis, dragging, logging, and .NET interface are also supported for this subject area. The main novelty of the three-dimensional solver is appearance of interval angular dimension. In order to implement it, we had completely rewrite the formulations of driving angular dimensions so that they all now have same range of allowable angle values that equals to pi, regardless of whether the angle was set with or without the rotational axis. To set the interval angular dimension, the overload of the at-angle function with an interval argument appeared in the API. Thus, three-dimensional solver now supports both linear and angular interval dimensions. When designing solid assemblies, it can be very important to know that the geometric object is fully defined. The well-defined function in our API is responsible for these diagnostics. Previously, it often gave incorrect results. As a result of our improvement, it now gives correct results in almost 100% of cases. Solver is a complex product, and we are often asked how to implement it in existing graphic user application. In order to simplify our customers' work, we have prepared an example of implementing three-dimensional solver into application using C3D Vision and Qt libraries. This example is now available in the C3D Vision samples library. The code of the example is open source and can be used by you at your discretion. Our strategic plans for the future are development of advanced degrees of freedom analysis in three-dimensional solver, support for splines in three-dimensional solver and auto-constraints in two-dimensional solver, as well as further development of examples of solver implementation in user applications. You can learn about our immediate plans from our roadmap, which is available on our website. Thank you for your attention. You can always contact me using the contacts listed here.